Hubble's images were too blurry. JWST has now used its near-infrared camera, NIRCam, to investigate this discovery in more detail. The spectrometer, which can measure infrared radiation in particular, showed that the scattered light is indeed a separate galaxy that appears very small and shallow. Further analysis now reveals how this galaxy was built and what stars and elements it contained. The upstream galaxy cluster SP J0615-5746, itself about 4 billion years old and containing thousands of galaxies, acted as a gravitational lens. It spans several million light-years, which explains why this cluster has such a large size and gravity. Gravitational lensing is the wealth of science. Thanks to them, we can also study smaller objects, such as the Arc galaxy cosmic gems. Thanks to the study of this galaxy, astronomers can now look back about 97% of all cosmic time, which puts us roughly at the time limit of the observable universe. However, we must remember that we are talking about the observable universe. That doesn't mean there isn't more. It's a fascinating question these days: how big and how old is the universe really? We thought it was 13.8 billion years old, but now we see galaxies that existed as early as 300 million years after the Big Bang. This cannot be true, and we have to assume that the universe is much older or even infinite. That would mean we still have a lot to discover. The protoglobular clusters JWST, which formed only about 290 million years after the Big Bang, are considered to be the precursors of today's globular stars, consisting of hundreds of thousands of stars. By observing protoglobular clusters in this early galaxy, scientists hope to gain valuable information about the conditions and processes of star formation during this era. At this point, every clue is important if we want to know what really happened at that time and whether these galaxies are really young galaxies. Clusters are very interesting because they formed from dense clouds of gas and started forming stars very quickly. JWST again used its NIRCam to observe and analyze these early structures with high precision. Spectroscopic studies have been able to determine the properties of these protoglobular clusters, which provide new insights into the composition and evolution of early star clusters. The study of protoglobular clusters in distant galaxies not only helps us understand how the first structures of the universe formed, but also provides valuable clues about how matter in general formed. Once we understand this, we will be much closer to the origin and design of the universe. The researchers also hope to use the distribution and dynamics of protoglobular masses to find clues about the distribution of dark matter in these early galaxies. Dark matter is believed to have had an important influence on the evolution of galaxies and constitutes a large part of the matter in the universe. But we still don't know for sure if it really exists and what its exact physical characteristics are. Last but not least, protoglobular clusters in the cosmic jewel Arc galaxy should provide new insights into the timing of reionization. During this time, the universe is thought to have been permeated with neutral hydrogen, which later ionized and led to the cosmic dawn. Imagine an infinite universe, it couldn't be dawn. But until now this idea has been an integral part of our cosmology. Let's begin the journey together to this theoretical cosmic dawn. Scientists consider this time a decisive stage in the history of the universe, approximately 300 to 1 billion years after the Big Bang. There was a transition of the universe from an opaque state to a transparent state. The dark universe was still dominated by neutral hydrogen, it was like cloud soup. Then, with the formation of the first stars, ionization began and it became bright. The universe became brighter as a result of chemical processes and light could spread freely. Scientists call this time the cosmic dawn. Time before that was opaque, and since we could only observe visible light with our telescopes, there was little hope that we would ever see beyond the cosmic dawn into the cosmic night. Scientists envisioned the scenario before reionization as follows: the Big Bang was the launch weapon about 13.8 billion years ago. From the second 0 to 20 minutes after the Big Bang, the nucleosynthesis of the Big Bang took place. In the first minutes after the Big Bang, the universe was very hot and dense. In this phase, the first light elements were formed, consisting mainly of hydrogen and helium, with minor amounts of lithium and beryllium. That phase ended when the universe cooled to the point where nuclear fusion ceased in the superhot primordial soup, approximately 370,000 years after the Big Bang. A period of recombination followed and the universe cooled, resulting in the formation of neutral hydrogen atoms. This epoch marks the time when the universe began to thin out a little, because photons were no longer constantly colliding with free electrons. It was this recombination that produced the radiation that we can still measure today as cosmic background radiation. At that time the universe was still dark, there were no stars or light. The Dark Ages lasted about 370,000 to 300 million years after the Big Bang. During that time, the universe was filled mainly with neutral hydrogen and helium. The temperature of the universe continued to fall, and the first structures formed under the influence of gravity. The cosmic dawn began when the first stars and galaxies formed. The first stars are often called population 3 stars. They were very massive and short-lived. They produced large amounts of ultraviolet light that could later ionize neutral hydrogen. As the intergalactic medium ionized, radiation from the first stars spread. Initially, ionized bubbles formed around the first light sources, and over time these bubbles merged and the universe became increasingly transparent. The chemical processes during reionization were complex. The ionizing radiation, which was mostly in the ultraviolet range, had enough energy to knock electrons off hydrogen atoms and ionize them. In addition to hydrogen, the freely available helium in the universe was also ionized, but these processes occurred at completely different energy levels and did not have the same effect as hydrogen ionization. However, recent discoveries by the James Webb Telescope cast doubt on this theory. We now know of galaxies so far away that their light originates less than 300 million years after the Big Bang. One of these galaxies is JWST 14, but there are others like the Macy's Galaxy or Sirius 9336 that are very old. They all have a redshift of about 14, which means they have existed at one time, going back to the Dark Ages or even earlier. These discoveries overturn our previous cosmological models. According to these models, such massive and bright galaxies should not have existed in the universe at such early times. The existence of these galaxies now means two things: either the formation processes of stars and galaxies happen faster and in a completely different way than previously thought, or the universe is much older. Nowadays, scientists are busy trying to reconcile the latest discoveries with old theories. Where can there be mistakes? How did the old models appear in the first place? How did scientists in the 1920s and beyond arrive at these structures, and were the methods correct? All this makes for an exciting science thriller, and no one knows at the moment how this thriller will end. Are we getting a brand new physics? Do we have to consider that the universe is infinite? Or have our scientists overlooked some force of nature? It is certain that this scientific revolution will forever change our view of the world.